Okay, welcome back everybody. I wanted to do an example of trig sub. So recall the following. If we have a form like this, where it's the square root of constant squared minus sort of variable stuff squared, we want to make the following substitution. So u is equal to a sine of theta. The reason why we make this substitution is when we plug this in for u, we get a Pythagorean identity that simplifies the radical. In the second form, we've got the square root of u squared minus a squared, where u is variable stuff and a is constant stuff. We make the following substitution, so u is equal to a secant of theta. Because when I plug that in, I get an identity that simplifies the radical. So lastly, we have the square root of a squared plus u squared, where a again is constant stuff and u is variable stuff. And we make the substitution u is equal to a tangent of theta, because again, when we plug that in for u, we get a Pythagorean identity that will simplify the radical. So with that said, let's dive in. Let's do an example. All right, so let's say we want to compute the integral of 1 over the square root of 16x squared plus 9 dx. So we have to look and see which of the forms that's in. So this looks like it's in a tangent form, right? Because, well, all of this, including the 16, so this would be u squared, so u would be 4x. And this would be a squared, so a would be 3. And so if I have a u squared plus a squared form, clearly a tangent substitution. Okay. Don't let it bother you that the u stuff comes first. Remember, by the commutative law of addition, this is the same thing as this, right? So in that way, they match. Okay, so let's carry through with our tangent substitution, and let's see what happens. So the form that we want to use is u is equal to a tangent of theta. So what's playing the role of u squared? Well, all of this right here is u squared, so u is 4x. What's playing the role of a squared is 9, so a must be 3. Well, we also need to get rid of dx. We want something that's in terms of our new variable theta. So maybe we should isolate x, and then we'll take the derivative, and that will help us get rid of dx. All right, so if I compute the derivative, so dx is equal to 3/4 secant squared of theta d theta. And this is nice because I'm now able to change all my x stuff into theta stuff. And, well, I could plug this in for x here, right? And that'd be fine. I deal with some fractions and some canceling. You could do that. Or I can be a bit clever, because if I take this and I square both sides, notice what it gives me. It gives me that 16x squared is equal to 9 tangent squared of theta. That means I can directly replace this with this, and that seems really handy. So let's go ahead and do it like that. Okay, so goodbye, 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 16x squared. Hello, 9 tan squared of theta. That seems nice. We've got a plus 9 from before, so yeah, that was replaced with that. And then dx. So here's a mistake you want to avoid. Don't forget the dx. Often I see students will forget the dx, and their integral will it'll be wrong, it'll be something they can't compute, they'll trivialize it, and they won't use the techniques we intended. So you want to be careful. Don't forget this. Okay, so in for dx goes this entire quantity right here. So that's exactly 3/4 secant squared of theta d theta. That seems good. So now what I'm going to do is I'm going to factor out the 3/4 here in front of the integral. I'm going to factor out a 9 here. I'm hoping to get a Pythagorean identity. And then you're going to see me place secant squared of theta and d theta up top. Okay, so 3/4 factored in front. I've got my secant squared of theta d theta here. And then as promised in the radical, I'm factoring out the 9. And that's going to leave me with tangent squared of theta plus 1. And that's really nice, right? That's a Pythagorean identity. We know that tangent squared of theta plus 1 is exactly secant squared of theta. Okay, so that's going to give me 9 secant squared of theta. Okay, so now technically, if I took the square root of something squared, I would need an absolute value. But we're doing this process with the understanding that we're restricting theta. We often don't write it, but the understanding is when I when I make such a substitution that it's with this restriction. Okay. Okay, so that's going to allow me to not have to write my absolute values here. So now I'm going to take my square root with the understanding that we've restricted theta. Square root of 9 is 3. That's going to be a downstairs 3. So let's write it like this. And so that's going to give me a secant squared of theta over secant of theta d theta. These will reduce. That seems pretty nice. So what do we have here? It looks like a quarter. We've got the integral secant theta d theta. So that reduced to a classic form. So that's really nice. So this is the natural log of the absolute value of secant of theta plus the tangent of theta plus c. But of course, we know that we're not finished yet, right? Because we started with variable x. We want to end with variable x. This is an indefinite integral, right? So we want to go back to the original variable. So the question is, how do I go from theta land back to x land? Well, the idea is pretty clever. What you do is you go back to the original substitution. And you want to isolate your trig function. So going back to the original substitution, get your trig function by itself. So divide that 3 out. And you know, anytime I've got trig function equals fraction, I can turn that into the sides of a right triangle. Because just think of how tangent's defined, right? It's opposite over adjacent. So that's going to be the side opposite theta. That's adjacent theta. And this is powerful because this allows me to relate x's to thetas, right? So here's theta. So I've got opposite over adjacent. And to find the missing side, I just use the Pythagorean theorem, right? So a squared plus b squared equals c squared. So that's 16x squared plus 9 equals c squared. And so the square root of 16x squared plus 9 is c. Don't call that 4x plus 3. That's not 4x plus 3. You can't take square roots over pluses and minuses. I've seen you try. Doesn't work. Okay. Cool. So we're pretty much there. So now we just have to take the secant and the tangent. We actually have the tangent for free if you think about it. But really we have to take the secant of the angle. But that's not a big deal because secant's just the flip of cosine, right? So just take the cosine and flip it. That's going to give you secant. So if I want the secant, I should do hypotenuse over adjacent. Okay, that seems okay. Hypotenuse over adjacent. Okay, and then tangent is right here. You could also use your triangle, but it's right there. That's going to be 4x over 3 plus c. And you have common denominators. So you can write that as a single fraction. That seems pretty nice. So that's all over 3 plus c. So you could break this up more using laws of division with logarithms, but I think that's perfectly fine.